On March 6th, we started talking about linear transformations. This video is a review of what we talked about in that lecture. So suppose we have two vector spaces, V and W, and we have a mapping, L, that sends V into W. Well, we call this mapping a linear transformation if the mapping satisfies two conditions. The first condition is that when you take a scalar and multiply it by a vector in V, and you apply the mapping L, it's the same thing as applying the mapping L to the vector V and then multiplying by the scalar. The second condition is if you add two vectors in your vector space and apply L, it's the same thing as applying L to both of the vectors and then adding them in W. So this right here, this alpha times V, is inside V. But this is a vector inside W. V1 plus V2, this is inside V, but when you apply L to it, you're inside W. So here you're adding inside V, but this is inside W when you apply L to it. This is inside W. And so now you have addition in the vector space W. So here you have addition in this vector space V, and here's addition inside W. All right, let's look at some examples. I'm going to have some examples and non-examples. The first one is the mapping R3 to R2, where I take a vector, so our vectors in R3 look like this, and our vectors in R2 look something like this. So V is R3 and W is R2. And what we're going to do is for any vector in R3, we're going to send it to this vector in R2, where I take x1, I send it to x1, and then I take x2 and subtract x3, and that's the second component in our vector. Let's see if this is a linear transformation. So what we need to check is that L of alpha times V is alpha times L of V, and we need to check L of V1 plus V2 is equal to L of V1 plus L of V2. Let's start with the first one. So I'm going to apply alpha to a vector. So let's let our vector be this x1, x2, x3. So L of alpha x1, alpha x2, alpha x3 is equal to, well, we're just going to follow the rule. The rule says we take this part and place it here. So we have alpha x1. And then we take the second part and subtract the third. So we have alpha x2 minus alpha x3. And now we're going to compare it with alpha times L of that vector. Notice that in R2, you can pull out the alpha, and you get x1, x2 minus x3. So this is L of alpha times V, and this is alpha of L times V, L of V. So the first condition is satisfied. Let's check the second condition. So I'm going to put 1 here, 2 here. I need to check that if I add two vectors in V, it's the same thing as adding their mappings in W. So we need to call this vector something. I'm going to call this vector x1, x2, x3. You can call it y1, y2, y3. I'm going to say z. So let's say that this is L of x1 plus z1, x2 plus z2, x3 plus z3. And that's because when we're in R3, that's how we add two matrices. We just add their corresponding entries. Now we're going to apply L to this using the rule stated right here. So we keep the x1 and then we take whatever's in the x2 spot and subtract the x3 spot. So following that rule, we keep this piece, which is x1 plus z1. Then we take this piece, x2 plus z2, and subtract x3 plus z3. Okay, so then this is equal to x1 plus z1, x2 minus x3, plus z2 minus z3. Notice that I distributed this negative, and then I kind of group the x's together and group the z's together because I want to pull these apart. Remember that you can break these matrices up into x1, x2 minus x3, plus z1, z2 minus z3. And this is precisely L of v1 plus L of v2. Because in the beginning, remember that I had this vector v1 and v2, and I said v1 was equal to this. So let me write it like this. v1 is going to be x1, x2, x3. v2 is going to be z1, z2, z3. I applied the mapping, and when I applied the mapping, I was able to break it up into these pieces here. But notice if I just had v1 and I applied L to it, I would have, because v1 is x1, x2, x3, follows the condition, and here v2 is z1, z2, z3, and here's the condition of applying L. So I have that when I apply L to v1 plus v2, I get L of v1 added to L of v2. So this is a linear transformation. It passes the two conditions we needed to check, which were that if we multiply by a scalar, it's the same thing as pulling the scalar out and then just applying the transformation. And when we add two vectors together and apply L, it's the same thing as applying L to both of the vectors and then adding them together. So this is a linear transformation. Let's try another one. So I'm going to erase this so we don't see that anymore. Okay, so here I have a mapping that takes R2 to R2. And I want to know, is it linear? And how I'm going to map a vector in R2, how I'm going to send it to R2 again, is I'm going to keep the first entry, but then I'm going to stick a 4 here. So for example, L of 2, 9 will go to 2, 4. L of negative 1, 1 will go to negative 1, 4. So this is how I'm mapping. For any vector you give me, I can tell you where I'm going to be sent. Okay, so is it linear? Well, let's check our two conditions. The first one is L of alpha v equal to alpha L times L of v? So here I'm going to let v just be x1, x2. Let's see. So L of alpha v is equal to L. I'm going to multiply everything by alpha. And then I'm going to apply L. And L says I keep what's in the first entry here, alpha times x1, and then I put a 4 here. Now, is this the same? Is this equal to alpha times L of V? Let's see. Alpha times L of V is alpha times L of x1, x2, which is alpha times x1, 4, which is x1 times alpha, and 4 times alpha. Are these the same? No, because if alpha is anything other than 1, you won't get a 4 here. If it was 2, you'd get an 8, and that's not the same thing as what you see here. So they're not equal. So this is not a linear transformation. You only have to check if one of them fails. Both of them could fail, or just one condition could fail. But as long as one condition fails, then it's not a linear transformation. To check that it is a linear transformation, it has to pass both of them. But if it's not a linear transformation, it just needs to fail one of them. So once you have that it fails one, you don't have to check the other condition. If you want, you can check the other condition, and I'll go through it really quickly. So let's say L of V1 plus V2. Well, this is going to be L of, I'm going to do the same thing where I label this X1 and Z1, X2 and Z2. Well, then this will be sent to X1 plus Z1, 4, by the rule of the mapping L. But then if you check L of V1 plus L of V2, you'll see that this is sent to X1, 4, and this one is sent to Z4, and you get X1 plus Z1, 8, and these two, let me star that, this one and this one are not equal because I have an 8 here and I have a 4 here. So this one is not satisfied either. But you only have to check one. It doesn't matter which one you check if it's not satisfied. But if you want to check that it's a linear transformation, they both have to be satisfied. Okay. Here's another example. Here I'm taking Rn to Rm. Now N and M can be the same or they can be different. But how I'm going to take Rn to Rm is I'm going to multiply any vector V in Rn by a matrix, a fixed matrix A m by n. So I'm going to put right here, this is fixed. So you can come up with any matrix you like. For example, you can say A3 by 2, 1, 1, 1, 1, 1, 1. That's a 3 by 2 matrix. And you're going to take R3 into R2. So your vector V could be x1, x2. Sorry, this should be, you're taking R2 to R3. See, here's the N, here's the N. So this is a 2, and I need to take a 2, R2 to R3. And all you have to do is say 1, 1, 1, 1, 1, 1, x1, x2 will be x1 plus x2. In fact, you'll have that 3 times. So you can come up with any matrix you like. The n part will be what you're taking. So if it's like 5, you would take R5 to whatever number's here. If it's 3, then you would be taking R5 to R3. So you can come up with any matrix you like. This is always going to be a linear transformation. And we can check that. So just erase all this really quickly. So let's check that it is in fact a linear transformation. I'm going to rewrite the condition here. L of V is equal to A times V. Well, we need to check that if we multiply a scalar by V and I apply L, is this in fact, so I call it A. I get A and alpha confused sometimes, but it's alpha. if I take alpha and multiply it by v and apply L, is the same thing as applying L to just v and then multiplying by alpha. Let's check it. So L applied to alpha times v is A times alpha times v, but we know because of matrices, we can pull that alpha to the outside, and here you just have alpha times L of v. Let's check the second condition. So that's satisfied, the first one. If we add two vectors and apply L, is it the same thing as applying L to the vectors and then adding them? Well, A times v1 plus v2, we know because of matrices, what we know about matrices is we can distribute that matrix, and that is indeed L of v1 plus L of v2. So this is a linear transformation. It's really interesting. Any matrix you can think of is a linear transformation from Rn to Rm. So come up with anything you like, any matrix, that is a linear transformation. So we're going to look at a couple of examples of vector spaces that are not Rm and Rn. For example, this is one I did in class. We have the vector space V equal to the space of continuous functions on the interval 0 to 1. So that's what that little c means. They're just continuous functions on this interval. And the linear transformation is going to take this vector space into the real numbers. And how we're going to do that is for any function you have, we're just going to take the integral and evaluate it from 0 to 1. Remember, for a function to integrate a function, all you have to have is that it's a continuous function. So let's check to see, is this a linear transformation? I think I'm going to abbreviate this for now on as LT, just so I don't have to write all of that. Okay, well, what do you need to check? You need to check that L of alpha times some function is alpha times L of the function. And you also need to check that for any two functions you give me, if I apply L, it's the same thing as applying the transformation and then adding the functions together, or adding the real numbers together, because these are going to be real numbers. You know, something we talked about in class is we can actually combine these two into one step to check. All you have to do is check that this is equal to this. So you can check both of these, that's fine, or you can check them in one step. So I'm going to do one step. So let's see. Is L of alpha times f plus g, is that equal to alpha times L of f plus L of g? What do we know about integrals? Let's do the left hand side. This is the integral from 0 to 1 of alpha times f plus g of t dt. But what you know from calculus about integrals is that integrals break across a sum. So this is the integral from 0 to 1 of alpha times f of t dt plus the integral from 0 to 1 of g of t dt. And you also know that if you multiply a function by a scalar, you can pull that outside the integral. So here you have alpha of L of F plus L of G. So this condition is satisfied and it is a linear transformation. Another strange linear transformation that we're going to look at involves derivatives. So suppose you have twice differentiable continuous functions on this interval 0 to 1. So here the c was continuous, and this 2 means that we can take the derivative twice, at least 2 times. You can maybe take more derivatives, but it can be done at least 2 times. And here I'm going to take the vector space V to itself. And how I'm going to map the vector space V to itself is for any function you give me that's twice differentiable and continuous on this interval, I'm going to take the second derivative, add it to 3 times the first derivative, and then subtract the original function. So I want to see if this is a linear transformation. Is this linear? Okay, well, all we need to check is this condition here. So let's apply it. So L applied to alpha times F plus G is equal to, well, I'm going to take alpha times F plus G, second derivative, add to it 3 times alpha times F plus G, the first derivative, and then I'm going to subtract alpha times F plus G. Okay, well, what do we know about derivatives? You can break the derivative, so you can distribute this derivative to the inside of this function here. So you get alpha times F, second derivative, plus G, second derivative, plus 3 times alpha F derivative plus 3 times G derivative minus this negative is sent to everything on the inside of that parentheses. Okay, and we also know that we can take a scalar outside of this derivative, so we can take that alpha out. And I'm also going to group all the things with F together, and then I'm going to group all the things with G together. So I have this alpha F double prime, cross that out, plus 3 alpha F prime, and then I have a minus alpha F, and then I have plus G double prime, 3G prime, and a minus G. And then that, let's put it in black. Notice that each one of these has an alpha, so I can pull that out, and that's L of F plus L of G. So this is a linear transformation. The interesting thing about this, and we're going to learn this in the next video, is that all linear transformations can be represented as a matrix times a vector. The last thing I ended on in the lecture on that Friday before spring break was we talked about just a couple of important properties of linear transformations. The first one is that the zero vector in V, so this little v means that this is the zero vector in V. If we apply the linear transformation to it, we're going to be sent to the zero vector in W. Now, lots of things can be sent to the zero vector in W. For example, if you take R2 to, let's say R, and we say x1, x2, we're just going to send everything to 0. Every single thing being sent to 0, including the zero vector. So what this property is saying that, there might be other things sent to the zero vector, but for sure, one thing that is absolutely sent to the zero vector is the zero vector in V. So you can see L of 0, 0 is going to be sent to 0 along with everything else. Now this is a very important property because sometimes vector spaces, all you have to check is if the 0 vector is being sent to the 0 vector. If you're not being sent to the 0 vector, it's not a linear transformation. So remember that example we did earlier, which was, I think it was, we took R2 to R2, and we said L of x1, x2 is equal to x1, 4. Okay. We said that this was not a linear transformation. And the reason it's not a linear transformation, we showed that if we apply L to alpha of x plus y, we don't get alpha of L of x plus L of y. You could do them one at a time. You could show that L, I think this is what we did, that this isn't equal. But you could show that this one's not equal as well. But a really quick way to show that this is not a linear transformation is to see that L of the 0 vector is sent to 0, 4, which is not equal to the 0 vector in R2. So you could tell me that this is not a linear transformation because the 0 vector is not sent to the 0 vector. Now sometimes the 0 vector is sent to the 0 vector and it's not a linear transformation. For example, let's say L sends R2 to R2, and we have L of x1, x2 is equal to x1 squared, x2. This is not a linear transformation. You can just check that L of alpha, let's call this vector v, this is not equal to alpha of L of v. If I put an alpha here, I'd have an alpha x1 squared, so I'd get an alpha squared. But if I multiply by an alpha, I wouldn't have alpha squared. So this is not a linear transformation. However, the 0 vector, if I put 0, 0 here, it is sent to the 0 vector. So just because the 0 vector is sent to the 0 vector doesn't mean it's a linear transformation. So it's not enough to just check this. This is just one thing that you can quickly check to see if it's a linear transformation. So if it fails, that the 0 vector is not sent to the 0 vector, it's not a linear transformation. If the 0 vector is sent to the 0 vector, then it could be a linear transformation, and it could not be a linear transformation. You need to check the two conditions that, the scalar multiplication and the addition of vectors, that thing holds when you apply the linear transformation. Okay? The other thing that's important that happens in a linear transformation is that linear combinations of vectors in your vector space V, those are sent to linear combinations of vectors in your vector space W. So all of this is a linear combination in V, but when you apply L to it, you're sent to a linear combination in W.